3D, if you haven't tried drawing in 3D, you learn really quickly why we use things like Calcplot 3D. It's not as easy as drawing a graph in 2D, but I do want to hit a couple of things. We're going to start off in rectangular coordinates. We will talk about different coordinate systems later this semester, but a little bit of review. In 2 dimensions, we identify a point as X and Y. So it is some horizontal and vertical distance away from the origin, right? So we have some point, it's some X, Y, and it lives out in the 2-dimensional plane. The same thing is basically happening in 3D, but we have another axis we have to think about, all right? And so this is our conventional way of drawing the 3D axes with the X and Y coming out. Sometimes you'll see the Y go completely horizontal. Excuse me. The Z is we think of as the vertical, and then we have the X kind of coming out of the board at us. You know, yeah, it's kind of like I said, it's the conventional way. And typically, if we draw something, we only draw the positive axes because, as you can imagine, if you start to draw the negatives, it gets really convoluted. Now, a point here now is in 3 space, so it has a X, Y, and a Z component. So it still has an XY in the XY plane, and then it's some height above that XY plane. So, you know, one way of conceptualizing what a point looks like, it's the corner of some kind of rectangular box. Again, drawable, but not as quick, not as easy to draw as it is in 2D. And, you know, before those lines were in there, right? Where is that point? Is it, what side of the y-axis is it on, right? Is it in the X, positive X, or is it in the negative X? So there's a lot of visual things that aren't as simple as they were in 2D, which is why we're not going to spend a lot of time drawing in 3D here. But we need to be able to recognize that stuff, and that's where Calcplot 3D is going to come in. So what we're going to do today is I'm going to show you a few standard shapes. I want to get you just thinking about this stuff. And we're going to play around with Calcplot 3D. So what I need to do, give me just a sec. I got to do a couple things here. And all right, so we're going to have 2 things going on simultaneously, and all right, so I'm going to show you a little bit about how Calcplot 3D works. Oh my goodness, you don't get to see those guys. Ah, they're over here, that's why. Give me just a second. Okay, there we go. That's what I want you guys to see is Calcplot 3D. Okay. So we need to think about what these shapes are going to look like in 3D. For example, the plot of z equals 1. Now in 2D, if it was just y equals 1, it makes a horizontal line, right? Well, think about what a line would be in 3D. What do you think a line is in 3D? It's a plane. There is a line in 3D that would be just a line that would kind of be like a rod. But the way a 2D line transforms into 3D is as a plane. So in Calcplot 3D, and for those of you guys at home, if you haven't brought it up, you can just search for Calcplot 3D. It'll be one of the very first options. Oh, and I got to make sure I'm using the right computer.
Put it in the chat for the people at home.
All right. Let me bring up a fresh one when we go back to that one in a second. So if you search Calcplot 3D, it's the one on LibreText. And this is always the standard graph that comes up, okay? And the equation for it, you can see over here on the left-hand side. Let's get rid of that. All right, first up, when we're talking in 3D, now when we're in 2D, a lot of times we say a function is y equals, like y equals x squared, something like that. So in 3D, the equivalent of that is z equals. So if we want to plot the plane of z equals 1, we just bring up function z equals. They have a default in there, and if you guys ever want to play around, they have a whole bunch of, these are all pre-built ones if you want to see what they look like. But for today, we just want to know what z equals 1 looks like. It is a plane that goes through the point where z equals 1. So what this is a collection of points that are all 1 unit above the xy plane. So that's what z equals 1 is going to look like. So what would have been a line in 2D is a plane in 3D. And we'll see that with linear functions as well. Now, y equals 1 will also be a plane, except now it's going to be confined to the place where y equals 1. And if you go to select and you scroll down to function, you see how there's some other functions here at the bottom. Here's where you can put in 1 for y equals. And that gives us a plane of y equals 1. We can do the same thing for x equals. So we can do any of the 3 variables. We can do a function in terms as z equals, x equals or y equals. All right. Now we're not going to hit everything that Calcplot3D can do today. I just want to give you enough to do what we're going to look at today. We'll, when we get into more interesting stuff, we'll revisit Calcplot3D. But I want to show you a few things that are pretty cool. Here's a cool one. All right, we want to talk about the plot of x squared plus y squared equals 1. What does x squared plus y squared equals 1 look like in 2D? It's a circle. Tell me more about that circle. Radius 1, where's it centered? Origin, right? Okay. If there's nothing else going on, when we transform this to 3D, what happens with that circle is it basically adds in the z and it comes in and out of the board, right? Yeah. So what this creates is a cylinder. Now let's talk about how to graph that though, because here's the thing. And sorry, computer. And here's the thing, and this is what you want to remember. When it's x equals z equals or y equals, we just saw how to do that. Notice this is not solved for x, y, or z. This is what we call an implicit equation. So if you go to your select menu, you see implicit surface. We'll go there. They've got one in there for us, but that's not what we're looking for. Let's put in the one that we're doing. Equals 1. Boom. There's our cylinder. But if we look directly down the XY plane, we're going to see exactly what you guys told me, which is that circle of radius 1. So anytime you're dealing with an equation that is not solved for a variable, you can always do it as an implicit surface. All right? Be the same way we do spheres. This is a cool one. Z equals x squared plus y squared. Well, we know y equals x squared is a parabola. So z equals x squared would be a parabola. Z equals y squared would be a parabola. So we put those in together. And actually, it's already in there for us. This is called a paraboloid, basically a 3D parabola. And, right now it is perfectly round, as you can see, but if you put a factor in front of one of these, you get an elliptical paraboloid. Bum, bum, bum. There's going to be a lot of cool stuff, and that's why, the next little bit I'm going to go through kind of quick, because I want to give you guys time to play with this program, because there's just so much cool stuff you can do. And it is fun, trust me. You guys will be using this at home. Remember, you don't have to draw any of this stuff by hand because this exists. This stuff did not exist when I took this class, so I'm jealous of you guys. Yeah, yeah, we had to do this stuff in chalk. You guys think you had it tough. All right. Let's all right, I want to talk about a few things. We'll come back to CalcPlot 3D a little bit later, but I just want to go over some stuff just so we have some common ways of talking about this. I am going to give you some formulas, some definitions here. Do not feel like you have to write any of this stuff down. Again, all the slides are available up and more. So everything I'm about to talk about is up there. I don't want you trying to write things down because I'm going a little bit fast. I also do not want you memorizing the names of these graphs that we're going to go over. That's not what's important. What you're going to do when you play with CalcPlot 3D is see, oh, hey, when I switch this parameter, this makes the graph do this. So that when you go see some function at some point, you'll be able to match it to the graph. Because, oh, it's got these characteristics. It's round here. It's got a curve here. It's got a hole here. That's what we want to do. Okay. First guy is the distance formula. This is in 2D. This is our Pythagorean theorem. This is nothing new. Well, you know what the distance formula basically gives us is the formula of a circle around the center x1, y1. Because what this is a collection of points that are all the same distance from x1, y1. We have a distance formula in 3D. It's going to look very familiar. It's that distance from the origin out to our point. Notice it was almost, these are exactly the same from our 2D. Now we have this third part here. Why am I telling you this? We might use the distance formula in 3D. It's not hard. It is just the Pythagorean theorem, but it's the same idea. If we set d to be a constant, then what we're looking at is the concentration of all the points that are the same distance from a single point. That creates one of our favorite 3D graphs, the sphere. All right, and just like a circle, we can move the center of the sphere around. The sphere, just like the circle is one of our easiest shapes in 2D, the sphere is one of our easiest shapes in 3D. So if we had a sphere with a center of A, B, C, this would be its formula. Now with the square root, think about what's going to happen. We're only going to get positive R values. So the way this is written would only give us the top half of the sphere. If we square both sides and do an implicit surface, that's when we get the whole sphere. Just like with the circle and that cylinder. So that's going to be the sphere of radius R centered at ABC. So I'm going over some basic shapes because these are going to be the ones that we revisit most often this semester, because what we're doing here is we look at stuff in a little bit more simplified form to show that all the theorems work. Then you go out and you work on much more complicated ones, but you know how the theorems work and how to use them because you've practiced them in simplified situations. Forgot about that. Cylindrical surfaces. We already saw one with the cylinder. A cylindrical surface is basically when a 2D graph becomes a 3D surface. So, and this is, guys, this is one I can't emphasize this enough. You're going to see some definitions in here. You do not need to know these definitions. So don't feel like you have to memorize them. I just put them in here because they're interesting. So there's a generatrix. That's the curve that generates the surface. So our cylinder that we saw earlier, the circle's the generatrix because that generates the whole cylinder in 3D. That generatrix moves around a directrix. For those of you guys who have seen conics, that term should sound familiar. That's what creates our parabola or circle, all our conic sections. Those 3D lines that make the 3D surface, those are called rulings. So where you're going to see these is in equations that only have two of the three variables. Remember the cylinder was x squared plus y squared equals 1. Z was missing. So it was a circle in 2D. When we added that z-axis, all it did was go in the z direction. That's what these cylindrical surfaces are. So here's kind of an example. We saw x squared plus y squared. There's your generatrix, the circle. And then these are your rulings, these lines in 3D. Okay. That's all that means. Again, you're probably not going to hear me use those terms again all semester, generatrix or rulings, but if you happen to see them in a text or something, I want you to just be like, oh, okay, I know what those are. I've seen them before. Here, z equals x squared. This is another good example. Notice there's no y. So this is going to be a parabola in the xz plane. But when we add that y axis, it's going to come in and out of the board. And then those are the rulings, are these parallel lines that create the surface. So that's just what those terms mean. All right. Last thing, again, guys, I do not memorize this stuff, but you're going to be plotting some of these in Calculus 3D. You're going to have my notes to go off of. There's not going to be something on a test that says, which of these is an ellipsoid, which of these is a hyperboloid. But quadratic surfaces are pretty cool in 3D, some of the shapes that we can get, and they all have a basic form. This is a quadratic. Remember, quadratic in 2 dimensions was ax squared plus bx plus c. This is what it is in 3D because we have the extra variable. This is the general form of a quadratic. I know it's messy and it is not something you need to memorize, okay? But having different coefficients are going to create different types of curves. Ellipsoid, hyperboloid of 1 sheet, 2 sheets, elliptic cone, elliptic paraboloid, and hyperbolic paraboloid. Those are the terms I do not want you to memorize. I'll never ask you that on a test. All right. So when we look at a 3D graph, because it's very hard to look in 3D, a lot of times what we do is we look at the traces. The traces are when we set one of the variables to be 0 to cancel it out, or set it to a constant to cancel it out. Because what that does is it turns our 3D graph into a 2D graph. And we can say, oh, in 2D, it's a parabola, so I'm looking for something with a parabola in its shape. Or in 2D, it's a cubic, so I'm looking for something that has a cubic in its form in the plane z equals 1. So that's one of our ways of taking the 3D function and making it 2D so that our visually we can better understand what's going on. All right, the ellipsoid is our most basic one. It's basically based off the sphere. This is its general form. And it's going to look something like this, like an egg. That's an ellipsoid. So this is when all three terms are positive, and the equation equals 1. And all 3 traces are ellipses, because if I were to cancel out, let's say we zeroed out the z term, we'd have an ellipse in 2D, x squared over a squared plus y squared over b squared equals 1. That's what a trace is. It's like when you zero out a term, what do you have? A hyperboloid of 1 sheet. Notice what changed. We now have a negative right here, just the single negative. And that changed to a hyperboloid where now along these vertical planes, we have 2 hyperbolas. But if you look at along the top, we have an ellipse. Because if we zero out the z, we have the formula of an ellipse. But if we zero out the x or the y, we have the formula of a hyperbola in 2D. So all 3 degree 2 terms are present. Again, this is not stuff I want you to memorize. You can use, anytime you're looking at this stuff, you can absolutely use the notes for it. So we got so again, this is how we use the traces to help us break down a 3D object to 2D, which is much more manageable visually. All right. 2 sheets, hyperboloid of 2 sheets. Notice now there are 2 terms that are negative. What does that do? It breaks the parabola into 2 pieces. All right. And now we have 1 trace as an ellipse parallel to the 3rd plane instead of in it. And then we still have two traces that are paraboloids, but it's that break in the one sheet versus two sheets. That's what's happening. Because of that extra negative, now we have a break between the two sheets. Elliptical cone, if we look at what's happening here, we have a plus and a minus, but now it's equal to 0 instead of being equal to 1. So what that's doing is that's forcing us to hit the origin, which is what's making these conical shapes. Now you've got ellipses on bottom and top. So if we look at the traces, we've got the ellipse, and then the other two traces are hyperbolas, but they hit that point at the origin because it's equal to 0. So it makes it more of a cone as opposed to that nice curved hyperbola shape. All right. An elliptical paraboloid, notice Z is no longer squared. So what that creates is the paraboloid that we saw earlier, and it's elliptical if the A and B's and C's are not in ratio with each other. So this is going to happen if you have 2 degree 2 terms and 1 non-degree 2 term. And the hyperbolic paraboloid, this is actually a pretty cool one. It's a lot like the elliptical paraboloid, but what makes it hyperbolic is the plus turned to a minus, and it creates a saddle, because what's happening is we got parabola, but then we have also a hyperbola in there when we zero out the Z. So, guys, again, I can't emphasize enough. I'm not trying to get you to memorize all these characteristics. This is way too much. I just wanted to introduce you to these because they do show up in the problems and in the text. And it does still give us a way to start to reason with these 3D objects that we're seeing now for the first time. Looking at the traces, looking for hyperbolas, looking for parabolas, looking for ellipses. Okay. One last thing I want to show you in Calcplot 3D, and then we will go on. And let's just do that. Nope, I did the wrong one. Okay. Last thing I want to show you. Okay. All right, easy fix. Okay. Now, we just looked at the hyperboloid, the paraboloid, and all that stuff. And did you notice in the slide how, I had the A, B, and C? Now, normally those are constants, right? And that makes the different shapes. One of the cool things about Calcplot 3D. So if I wanted to do, let's do just basic one. Let's do an ellipsoid. That's going to be an implicit surface. This is already almost, let's leave it as a hyperboloid. You can actually put those in. So A squared, this is pretty cool. B squared and C squared. And when I hit enter, there's my hyperboloid, but look at what it did for me. I can now use sliders and so you can see what changing A does. What does changing B do? What does changing C do? And I didn't spend a lot of time going over all the things you can do in Calcplot 3D, but notice right now I'm in between 2, 2, 2, and -2, -2, -2. Right here is, okay, if I wanted to see a little bit more of the graph, here's where I can format the axes. All right, so now it goes out to 5 and -5. So you can change the axes in there. We'll look at what some of these other ones do later here, like adding a point. We don't need that just yet, because right now I just want to get you playing with some of these curves. All right, and so we're going to go into the worksheet for 11.3, which I put somewhere. And you guys at home can bring it up. 11.2, I keep saying 11.3. You guys mind passing these around? What you're going to do for this worksheet is I've asked you to plot a few things in CalcPlot 3D, okay? These are not going to take you long. You don't have to do anything too fancy. But I want to talk about how you're going to get your participation points on these, because obviously you're doing them on the computer, you can't share them. So here's what you're going to do, because this is also going to be some practice for the take-home problems. Let's say my graph here is the graph for number 1, okay? If you go over here to the 3-line bar and you go to File, I can export that as a PNG. So that saved my graph, okay? Then what you'll do is you go to Microsoft Word. Let's get that one out of there. Let's just say this was number 1 and it was the hyperboloid. And then I'll just go ahead and insert my image. I can find it. Here we go. All right. And that's all you have to do. Okay, whatever it was, the point, put it in, type it in, put in your image. And when you're done, and this is important, I can't stress this enough, obviously save your Word document, but I want you afterwards, before you submit it, save it as a PDF. All right, and be sure to put your name in the file name, and then you can email it to me as an attachment. Okay, because that's going to be the same way you submit the take-home problems. So we may as well get used to it now. If you have questions about that, let me know, or let Professor Tar know. You can always email us if you have questions. So I know you're probably not going to get the worksheet done in the next 22 minutes. If you do, that's great, and you can submit and you're done. But if you don't, finish it up when you get home. Put your images into a Word doc, save it as a PDF with your name and the file name. And you can just email it directly to me. My email is up in more. And you don't have to memorize it, but just phil.clark@scottsdalecc.edu. I'll make sure that it's up there. It's also in the submission for the take-home problems, okay? Okay. Any questions about what we're going to do next?
So the worksheets are the ones that you said are just going to be extra credit at the end?
Correct. Okay. Yeah, remember, the worksheets are just for participation points. That goes for 11.2 as well. If you do not submit 11.2, there is no negative repercussion. But I would recommend doing it. It's going to get you some extra credit for the homework. Plus, it'll give you a little bit of practice using CalcPlot 3D, putting it into a Word doc and sending it over as a PDF. So we get a little bit of practice of what we're going to be doing later this semester. All right, guys, I want to let you, the rest of the time, we got 20 minutes left of playtime. Try to find some of this stuff on the worksheet, play around with it, have some fun. You guys can talk to each other. Hey, look at what I got. If you want to, we're going to create some cool stuff later this semester when we get into parameterized surfaces. So have some fun with this. We're going to revisit this program a lot because A, it's free. B, it's a heck of a lot easier than drawing this stuff by hand. And C, it does exactly what we need it to do. All right. So let's, I'm going to shut up so I can let you guys have some fun.
When you export as a PNG, obviously you want us to orient.
What was the question that was asked? We'll work out the system.